Okay, hello everybody. Thank you for joining for this last special information card at the much nicer time of your So I just wanted to say before we get started that there's lots of events going on this week, and I wanted to highlight the History, Philosophy, and Culture Day tomorrow. So it'll be in here starting at 10, and it'll be a bunch of presentations from various groups in the history, philosophy, and culture. So yeah, if you want to join, it's also hybrid, so you should have received an email to PHI emails about it, and we'll have the Zoom link there. But on to the main content for today. So we have our very own Don Pesce from the CFA, who will be talking about masers and cosmology. Can you click OK on there? And then
Yeah.
I'll turn it over to you.
Good.
Thank you.
All right, yeah, thanks, Helen, and thanks very much to Helen and Prashant for running this whole thing and for being very accommodating with my totally impossible schedule this semester. And it's nice that we're able to do this at 11. Wow, good showing. Yeah, so I'm going to talk about masers and cosmology, and then the clicker was working. So much for that. I'll just click manually.
I think it was just that the slides weren't selected, so it should work.
Yeah. Oh,
Clicking OK on Zoom.
yeah, I see. Got me Zoomified. So I don't know how familiar everybody is with astrophysical masers, so I wanted to start with this kind of perhaps surprising fact that despite how difficult it is to produce lasers on Earth, right? These things weren't invented until like the 1960s. They require some fairly sophisticated equipment. They certainly aren't just something you stumble upon in nature around here on Earth. It turns out that out in space, that's not the case. There are astrophysical masers that naturally arise in certain environments out there. And the particular one I'm going to talk about today that we use a lot as a tool for a number of things, and in particular in cosmology, is one species of maser that's emitted by a particular rotational transition of the water molecule. That's rest frame frequency is about 22 gigahertz because it's a spectral line. It's a transition fuse. And the wavelength is about 1.3 centimeters, so like an order of magnitude longer wavelength than something like the EHT typically observes at. And kind of like how there are two categories of black hole, we think of like basically roughly a stellar mass category and a supermassive black hole category. There's kind of a similar situation with these water masers. There's kind of a category that we see a lot inside of the Milky Way associated with individual stars, maybe a young forming star or a sort of more evolved star that has a very cool atmosphere that permits some molecular emission. But there's also another category that are associated with supermassive black holes, particularly the accretion disks around these supermassive black holes, these AGN disk megamasers, they're sometimes called. So this megamaser term that I will sometimes stumble into using, it comes because these two classes, one is about 1 million times more luminous intrinsically than the other one, so it gets this SI prefix mega. So this talk, I'm gonna focus on the application of these kinds of masers to cosmology. They have other applications that I'm not going to touch on, but I wanted to start with a little bit, actually, just take the excuse to do a little bit of diving into literature to talk about what were people's initial thoughts about using masers for cosmological applications, because I know how we do it now, right? But this wasn't always the way people thought to do it. In particular, the early days of thinking about how these masers could be used were very, they were in this context of masers as a very VLBI friendly observational tool, right? So masers, they're these non-thermal processes. They have very, very high brightness temperatures. So they're basically the only kind of spectral line emission that's typically accessible to VLBI observations. And this makes them very useful because when you have spectral lines, you have not only sort of spatial information, you also get velocity information through Doppler shifts. And anything with VLBI back in sort of the early days of VLBI was thinking about a lot of parallax, thinking about, okay, can we measure the distance to something using this bright maser? And that was really where most of the early thoughts about applications for these masers came from thinking of how can we use VLBI, this really great angular resolution kind of accessing tool, to look at these masers and apply them in some way to cosmology. So I'll walk through a few, what I think of now as more unorthodox ideas for using these things compared to what I'll eventually get to and spend most of the time on, which is the sort of approach we use nowadays. So the first paper I was able to find that referenced the use of masers in cosmology at all was actually this 1986 paper by Nikolai Kardashev, where this was really quite an interesting dive. So he recommended or sort of suggested maybe we could use the VLBI parallax measurements of these masers, but using a slightly different kind of parallax. Instead of using the parallax sort of made from the Earth going around the sun, he was saying, let's go use the parallax of the whole Earth Milky Way system moving with respect to the cosmic microwave background, and let's look at things very far away. So just think about this for a moment. the Earth going around the sun has a diameter of that motion about 2 AU, right? I guess definitionally 2 AU. And so you sort of get some wobble with anything that sort of is bounded by that maximum size. But the collective motion of the Earth Milky Way system through just the universe with respect to the cosmic microwave background is several hundreds of kilometers per second. It turns out that over the course of a single year, that effective baseline in distance, where it was to where it is a year later, is like 80 times larger than what you get just from the Earth going around the sun. So in principle, this could be a particularly large signal if you're looking at an object that is totally not participating in the same kind of motion that the Earth and the Milky Way are with respect to the CMB. And it does unfortunately turn out that even with this boost in signal, looking at extragalactic systems that are cosmologically relevant turns out to be a really, really tiny signal, and it's really hard to pick this up. And this plot here is one that I pulled from the from Kardashev's paper, showing how this the magnitude of the signal looks like in basically microarc seconds per year up here on the vertical axis as a function of the redshift of the source for 4 different choices of cosmology. At the time, they didn't know as much about the cosmology that we currently have, and this is even hard to do today with things like Gaia and really good parallaxes. So this is a measurement that turns out to be very difficult. One thing I did do was I tried to overplot our expectation for this signal from the current concordance cosmological model. I was very surprised that one of the curves that Kardashev shows looks really close to what we would get for today's cosmology. Because in 1986, there's a lot of things we didn't know. We didn't know the curvature of the universe at that time. We certainly didn't know that it had dark energy, like a positive cosmological constant, right? That wasn't discovered until the 90s. So I was like, what the heck is this model that he used? Model number 4 here. So it turns out this one has a flat universe, so it's really good. It has a negative cosmological constant, so that's unfortunate, and has a positive density of cosmological strings. Anyway, so we don't think that's how it really is, but it turns out you kind of mock up something similar to, at least for this particular observational signal, with a very different universal composition. Anyway,
Dom, I have a question on that.
please, yeah.
So here
This is the main part of the talk.
is it? Okay. So these are all FRW models, is that right? Or
I honestly don't remember. I
Okay.
believe they all are, but
Okay.
I'd have to check the paper. It's a short paper. It's pretty quick to check. I'm fairly certain this is all FRW cosmology, just twiddling around with the densities of various components.
and the fact that the signal is small is a statement about what the peculiar velocity
The
being
signal is small is just saying that when you have objects very far away, even having a sort of 100 AU baseline of motion is just not giving you a large angular
Okay.
separate motion. That's all. It's just a matter. It's a measure of the distance to these things. It's just extragalactic is really hard. It's really hard to measure proper motion. It's really hard to measure angular shifts. So another one of these sort of parallax motivated kinds of ideas for using masers is was actually put forward in a paper in 1988 by Mark Reed, Jim Moran, and Carl Gwynn. And this was the idea to measure something called this, known as the Van Manen effect, which is basically where you try to measure the angular rotation of like a spiral galaxy or something, and then you otherwise, in some other way, it determine its physical rotation using like Doppler shift and some knowledge of its inclination, and you just compare the angular motion to the physical motion and back out a distance that way. And so this is something where Jeremy Darling tried to pursue this for this is an image of the Andromeda Galaxy, M31, the nearest and brightest of these big spiral galaxies. And he was able to identify, I keep using this as a pointer, he was able to identify a number of water masers residing in the system. And that was in 2011. There weren't any follow-ups. I reached out to Jeremy, and also it turned out that Andreas Brunnthaler had been involved in this work. And they were both like, all right, well, the masers we were able to find in Andromeda turned out to be really faint, and they were even getting fainter with time. And the motions of those masers were actually primarily associated with local gas motions, like outflows and things like that, and not really with the global rotation of the galaxy. So it turned out this was probably going to be a really difficult measurement to make. And as far as I know, there's been no real effort to do this, even for M31, and M31 isn't even cosmologically relevant, or you need to be able to do it for something much farther away. So I think this signal is also really hard because of things like faint masers and just difficulty in actually measuring the rotation of the galaxy with them. You're not really guaranteed to have that. And then the last of the sort of unorthodox ideas I want to cover is also actually something that was posed by Jeremy Darling in that same 2011 paper. And this has to do with measuring. It's a pretty simple effect to understand, but it's something we don't normally think about cosmologically. Is the fact that is this sort of moving cluster effect is known as. It's the fact that when you have an object that's moving away from you, that object is getting smaller with time, right? Just apparent size is decreasing with time. We see this all the time on Earth, but we don't think about it, or at least I don't think about it very much cosmologically because the time scale should be so long. But in principle, because everything in the universe is receding away from us once you go out far enough, those things should be getting smaller in with time. And that effect, the sort of separation between any 2 points in an object that's receding from you should be decreasing with some factor that's proportional to the size of the object. So Jeremy did some calculations in this 2013 paper was really fleshed out. And, the same kind of story. The signal turns out to be really small. So even if you had sort of two masers on either side of a 100 megaparsec coherent thing that was moving really far away, it'd be on the order of like 1 microarc second per year type of signal at best. And so it's a really, really difficult measurement to make. And so this is another one where I haven't seen any actual measurements in the literature of it. All right, so that's my foray into unorthodox applications of masers for cosmology. I want to talk about the more sort of standard ones now, and the real breakthrough in understanding how we can use masers for cosmology came with the discovery of the now very well known NGC 458 galaxy, which was the first of these disk maser systems to be discovered. So the discovery observations for this system took place where were carried out by Mark Clausen, Fred Lowe, and Gary Heiligman. They were using the OVRO 40 meter dish at the time. So they were, these are the spectra there. They were able to take this sort of maser spectra. And the 40 meter dish is not, doesn't have a lot of angular resolution at a wavelength of 1.3 centimeters. Got a beam of something like 100 arc seconds. It was covering a really big chunk of the galaxy. They couldn't really tell where in the galaxy this emission was coming from at the time. They had this, familiarity with Milky Way masers, these ones that I was talking about. You have these star forming regions, young stars that exhibit maser activity. They're like, all right, maybe what we're seeing is a collection of many, many of these things in this other galaxy, this NGC 458 galaxy. And they're just all the aggregate emission from all of these individual star forming regions is sort of collecting up, and we're seeing it as a big, strong maser. But they did also allow for the possibility, it wasn't their primary interpretation, but they did allow for it, that this could be associated with the AGN. And the reason for that was because even at this time, there had been a couple of prior examples of maser emissions seen from galaxies that were known to host active galactic nuclei, in particular the Shinnis galaxy and the NGC 4945 galaxy. And also in the same paper where they published this one, they also detected maser emission from another well-known active galactic nucleus, NGC 1068. So they were like, starting to see some hints that maybe these AGN were also capable of producing maser emissions. They were like, maybe that's what it is here, but we think it's a starburst. Nevertheless, you can test that. You can say, all right, let's go pursue higher angular resolution observations and see really where this emission is coming from. That's what they did. They looked at it with the VLA, which is a connected element array, so really able to get much better angular resolution. They were able to show that the emission was coming from a region about a parsec across, just totally eliminating this starburst possibility. And then they also followed it up with some, one of these, I think, at the time, we don't appreciate it as much anymore, but really cobbled together VLBI observations. They sort of took the over a 40 meter dish. They asked some people at Haystack to join them, got something with the VLA, or that's right, this wasn't Haystack. This was OVRO, VLA, one of the dishes in Green Bank, but not the GBT, like the 43 meter dish that isn't operating anymore. And then I think Effelsberg, not Haystack, I'm sorry. But anyway, they got this like 4-station, just taped together VLBI array. It didn't do any imaging, but we're able to show that these features, right, the relative separations of these different spectral features were like under a milliarc seconds. They were really, really very close, very much not associated with an extended region of the galaxy, very much associated with the nucleus. And so this quote that I pulled from the Clausen paper I thought was really nice, saying, okay, this maser emission is coming from regions that are really, really tiny, not interstellar, not distributed like we see in our own Milky Way.
What is the time? I mean, does the time evolution of the emission distinguish between nuclear starbursts?
I think that's probably something that could have also been argued in favor of. You likely wouldn't get such, as you can even see it here. I mean, this is just two epochs. I don't remember what the separation is, but they are quite time variable. And I think there probably would have been an argument to make based on time variability alone. Of course, actually being able to see that it's spatially located at the nucleus is also very, very strong. But I think you're right, that the variability argument would have been really, it's hard to imagine having spatially distributed sets of emission, like across galactic scales, being this time variable and individual, unless you're really dominated by like one or two very small number of features. That's a good point, but that's not the argument they pursued. So this, for about a decade, is basically, modulo some variability is what we thought the spectrum of the NGC 458 system looked like. And then there was this remarkable discovery in 1993, a little more than a decade actually after these observations were first carried out. They were published in 1984, but the observations that Clausen and all did were in 82 and 83. So for about a decade, it was they thought there's just this one little set of features in here. But then there was this just new technology, a wideband spectrometer that they deployed on the Nobayama 45 meter dish. And they just thought, okay, well, let's test it out on a few things. There was no real expectation to see much. They were just testing their spectrometer and identified by pointing at 458 that these at about 1,000 kilometers per second to either side of this central set of features were two other sets of apparently maser features, some of which were also quite bright. These ones I'll refer to as the red shifted, those ones as the blue shifted, and the central one, I'll try not to, but I may say systemic features. And so this was really totally unexpected. I just want to point out that the bandwidth that the original spectrometer had just wasn't able to see it. They could have tuned it, right? If they had thought to do so. They could have tuned the spectrometer to either side and actually caught this other emission, but they had no reason to think to do so, right? Because you just look at, they're seeing the central set of features. It's nothing but blank sky on the other side, as far as they can tell. There's no reason to try to tune and look for other stuff. There's no expectation that this is there. So this was really, really exciting, because now you start to wonder what's causing these high velocity features. These are really 1,000 kilometers per second, the big velocity. And so, and also they did some VLBI with this original Nakai et al. 1993 paper between just one baseline VLBI between the Nobayama 45 meter dish and this Kashima 34 meter dish. They weren't able to detect the blue shifted features, but they were able to detect the red shifted and the systemic features, and show that they were located also very close to one another, at least within 50 milliarc seconds. So this caused a flurry of activity, because these high velocity features were totally unexpected, and it caused a lot of people to try to figure out what was going on in the system. So one thing was that they were able to identify, so Makishima et al. In 1994 pointed at this galaxy with an X-ray satellite at the time, this advanced satellite for cosmology and astrophysics. ASCA was the thing looking at X-rays, I guess. And they were able to identify hard X-ray emission from there. It turned out to have a very strong hydrogen absorbing column, which is something that actually ends up being relevant for these kinds of systems later on. I probably won't get into it, but they did see that, and they saw this bright, this strong hard X-ray emission, and able to confirm that it does actually host an AGN, a low luminosity AGN, but there is one in there. So again, this idea that the AGN is relevant came up. Hashik, Bond, and Peng had been monitoring this system with the Haystack 37 meter since basically its discovery. They've been monitoring just the systemic group of features, this central bit of features, and they had been seeing this effect that the velocities of the individual spectral features in that central group of features were drifting with time. The velocities of these features had an acceleration that was between 7 and 8 kilometers per second per year. And this plot is showing the line velocity versus the time here. And you can see that if you're tracking these individual features, they're exhibiting this kind of linear drift with time. And there's something they published as soon as they realized that this was really exciting, these high velocity features there. So local folks, Lincoln Greenhill et al., went ahead and did some similar monitoring of the high velocity features after they were revealed. Just a couple of years of it, they published in 1995 and showed that they actually didn't seem to be exhibiting the same kind of large acceleration. The systemic features had really strong apparent velocity drifts. The high velocity features didn't have any such thing. Over the course of a couple of years, they should have been able to see an acceleration as strong as 7 or 8 kilometers per second per year. And then Bill Watson and his student Brad Walden were the first to kind of put all these pieces together in something resembling what is pretty close to now the modern picture of how these systems work, which is there is a central massive object, we think a supermassive black hole, and around that is orbiting, in their picture, a ring of material that's producing the emission. We are the observers down at the bottom of the screen here, and we're seeing this system roughly edge on. And the emission that we're seeing in the center bit here, in the center of the spectrum, is coming from material in the foreground of the black hole, and the material to either side of the black hole is producing this high velocity emission. And this picture holds up pretty well, and I'll get into more detail on it, how we view it nowadays in just a few slides. But I want to pull out, these guys were proper theorists, and of course they immediately generalized this notion, saying there's probably more than just one of these objects. Go ahead,
Yeah, so I see that there are lines going all the way from the central black hole. Do they represent something, or the emission starts in the ring effectively?
Yeah, so there's a lot going on here that I was going to just gloss over. So one of the things they had here was that there's some emission from the central AGN actually that's seeding photons that are then stimulating emission through this gas, and it was said why this set of features were brighter than the other sets of features. There's a lot in here that probably doesn't hold up very well, but the general geometry does. Okay, so
what's the scale there in RG?
the scale in RG is about 10 to the 4.
Okay.
10 to the 5, that kind of range. I wouldn't know. I think maybe closer to 10 to the 4 in this system, but in general, between 10 to the 4, 10 to the 5. It's quite far out still. And so, okay, there were also VLBI results that came very quickly on the heels of this wideband spectrum discovery. So Lincoln Greenhill, same fellow as before, local fellow, went and reprocessed those, tapes together in 1988, VLBI observations, and actually was able to do some imaging with them with a fair bit of work. The Clausen et al. 88 observations of just the systemic features, just that central bit. And he was able to put together this image here on the left showing all the maser spots actually arrange themselves into a kind of linear structure on the sky. Again, they confirming much smaller than a milliarc second in collected size, but actually having some spatially resolved distribution. And when he plotted not just the locations, but the locations versus the velocities in this, what we call a position velocity diagram for these things, showed that was also showing a linear structure. So this is very consistent with what you would expect if these masers really were originating from a thin ring of material in the foreground, just like the Watson and Wallen paper predicted. So this is really a good piece of evidence that that's something like the right picture. And then very famously, the first full VLBI map of the system that included not only the systemic features, but also the high velocity features was published by Miyoshi et al. 1995. Yes, that same Miyoshi. And here's the map over here. You can actually see that the systemic features are the ones there in the middle. I'll color them in a moment, but so that you can get the velocities associated with spatial locations. The red shifted features are over there off to the left, and the blue shifted features here on the right, and they are spatially distinct. They're well within 50 milliarc seconds, like that original constraint, but they are spatially separated and resolvable with VLBI. And then the full position velocity diagram here. So here, that linear bit in the center is what we saw from the Greenhill et al. Paper, but now these high velocity features are showing really beautiful Keplerian rotation curves because they're radially extended now. And this is a distinction between what actually ends up being there in practice and what was predicted by the Watson and Wallen paper, which was prior to these observations, which is that the systemic features really do seem to be concentrated in a single ring, right? This linear feature sees this one annulus, one orbital radius that's producing the bulk of the emission. But that's not the case for the high velocity features. They really do seem to be radially extended, and you're getting this really nice curve that turns out to be very well modeled by a point mass potential. And it's sort of this simplicity of the system that turns out to be very important and makes it very powerful that we can model the dynamics here very well and get constraints on things like the mass and the distance to the system. This was also at the time, just given the mass and the enclosed density here, one of the best pieces of evidence in favor of supermassive black holes as the things that were actually the massive dark objects in the centers of galaxies. Okay, there we go. So here I'm going to color the points by sort of what velocity group they fall in: red shifted, blue shifted. I think I have it labeled. There we go. Red shifted, blue shifted, and systemic features corresponding to the three different components that we see there in the spectrum. And the idea is that we think, per the Watson and Wallen picture, but expanding on it a little bit, we think that these masers are living in an edge-on disk system. And so if we just look at the top part of that, we now, the observers are at the bottom, and they're distributed in this kind of way. This is how we think the masers are physically located or spatially distributed inside of the disk here. So the entire disk is orbiting around some central supermassive black hole, with the blue shifted and red shifted features sitting on what we call the midline of the disk, which is where the disk plane intersects the sky plane, and then the systemic features residing in front of the black hole with respect to our line of sight. So if these things are all orbiting around the black hole, their velocity vectors look something like this. And we think that the reason we're seeing emission in these particular locations has to do with this velocity structure and the fact that this is maser emission, stimulated emission. So the stimulated emission process requires photons, the amplification of this process requires photons to pass by inverted molecules, something that can actually produce emission, and to stimulate emission from those molecules. So every time you have a sort of seed photon passing by an inverted molecule, that photon can't be too far out of resonance with the stimulated emission, the molecule that wants to do stimulated emission, or else it won't stimulate that emission. And if you have a whole bunch of photons coming in that aren't stimulating emission, you're not going to get this exponential amplification that's the hallmark of a maser process, and you're not going to get very bright emission, you're not going to see anything. And so what we think is happening here is that the reason we're seeing masers in these particular locations in the disk is because these happen to be the places where the line of sight velocity gradient is smallest, right? So if you have an orbit here, the line of sight gradient of the velocity is smallest wherever our line of sight is perpendicular to those orbits or tangential to them, either parallel or anti-parallel to them. And so that's what's going on here. Oh yeah, go ahead, Daniel.
Yeah, so I guess observationally, what is setting the strong constraint on the radial position of the on-board site?
These ones.
Yes.
Yeah, so
because I totally understand how you get the radius of the off-axis emitter.
So it's primarily the accelerations that I was just talking about, right? So this acceleration measurements really say, and I'll get in a couple of slides, so like I'll have equations on here and everything.
Sure.
We can actually pinpoint exactly where that's coming from, but it's primarily the acceleration information. These things are all measured to have a particular acceleration
from repeated observations.
From monitoring over
I guess
multiple.
my impression is that a single snapshot would give you decent radial measurements for the off-axis emitters, but not the on-axis ones.
Yeah,
correct?
yeah, you have some very highly projected
That
version of
makes
the
sense.
radius there. Yeah,
Great, thank you.
that's right. And I just do want to point out again, this accelerations in this system, we can start to also understand from this kind of picture why we do see very large accelerations in the central set of features and why we don't see something similar in the high velocity features. And that just has to do with the orientation of the acceleration vectors for this kind of configuration, right? They're along our line of sight when the masers are in front of the black hole with respect to us, and they're perpendicular to the line of sight. We just don't see anything when they're oriented either side like that. All right, so getting a little more quantitative now, I want to walk through the same kind of cartoon picture. We've got masers in a circular orbits around a perfectly edge-on disk, and all these things can be and have been generalized, but this picture, I think, allows us to get most of the main ideas. And we're gonna just walk through what constraints we get from a single maser spot, which I'm highlighted in black here, calling its orbital radius r, its azimuthal location in the disk phi. So, it's an edge on disk. We only have access to the projected orbital radius of this thing. And so that's related to the actual orbital radius by some trigonometric factor, and then also by, because we're just measuring an angle, the distance to the system, which turns out to be pretty important. So this is r over d term over there. And these are order 0.1 milliarc seconds in separation for this kind of system. We also, for the velocity, only have access to the projected component, the line of sight component of the velocity. These turn out to be hundreds to 1,000 kilometers per second. And in this simple circular orbit around a point mass kind of situation, we can determine that orbital velocity in terms of the mass of the black hole and the orbital radius, just using simple high school level physics over there. And then likewise for the acceleration, we only get access to one component of it, the line of sight component of the acceleration, but we can relate it again to the mass and the orbital radius in this kind of very simple way. And now I just want to highlight what we typically have for systems, dynamical systems that we're trying to measure versus what we have here. Because here's where often we will have velocity information. And we may even be able to relate it to spatial information like radius and angular radius. And so we have something like that left term over there. But the radius we measure is angular, right? So it's really something that r is something like theta times d, right? So we really have something like a constraint on gm over theta times d. We measure v, we measure theta. So we have a constraint of something like m over d, right? This mass to distance constraint in that kind of velocity only setup. That's going to be very familiar to people who have worked at all on M87 or EHT-based mass measurements. This m over d degeneracy is something that sort of is a very standard problem in these kinds of modeling scenarios. But we're very fortunate in these cases that we also have access to the accelerations, because this is really what breaks this degeneracy. This is an m over r squared term here, toss that same theta d in there, and you have an m over d squared. So you have constraints on m over d and constraints on m over d squared. And those now break that, what would otherwise be a pure degeneracy. There's still high correlations but between those two parameters when you're doing modeling, but you actually are able to get unique constraints on both of them. And now I just want to do a little bit of parameter counting, because we have a measurement here, 3 measurements really, position, velocity, acceleration, but we also got a bunch of unknowns. We're trying to model this thing. We don't know the actual, initially, we don't know the actual orbital radius. We don't know its azimuthal location, r and phi. We don't know the distance of the system, d, and we don't know the mass of the black hole, m. So just counting this up, we have 3 measurements, 4 constraints. This problem is an under-constrained system. You're not able to uniquely back out values for the 4 things circled in red. But of course, we have more than one maser spot, right? If we have a second maser spot, we get access to 3 independent measurements, another theta, v, and a. So you get 6 measurements in total. You do get a couple additional model parameters, because then you don't know the orbital radius or the azimuthal location of that maser spot either. But the distance of the system is still the same, and the mass of the black hole is still the same. So those parameters don't sort of continue to add. So you actually only accumulate 2 more additional parameters you need to model. So then you have 6 measurements, 6 parameters, you're all good. And if you have a bunch more masers, like we really do in the system, typically dozens to hundreds of these things, the problem actually ends up being quite well posed, and unique solutions do exist for both the mass and the distance of the system, in addition to all these other nuisance parameters.
Dom, 1 second. Sorry.
Yeah, go ahead.
Just on the acceleration. So you're saying that you would have to monitor this for some period of time.
Yeah.
And assume that the maser activity in that region is approximately not changing at all.
Not sure what that
Because
means.
the-
It is
because this-
variable, but we're really just caring about like it can vary in flux density, but you just care about the sort of velocity drift of the maser, right?
Right.
Not its, if it varies in flux density, you tend not to be as worried
Fair
about
enough. So the
Yeah.
velocity, you like basically, even though the moving on Keplerian orbits, the change in that is not significant.
The velocity change is significant. We measure it as an acceleration.
Right. The change from the Keplerian value is not significant.
I see. Okay, the model is good at about the percent level. That's actually one of the dominant systematics at the end of the day, that it's not perfectly Keplerian. There is some effect, but it turns out in this system enters in at about the percent level. That's one of the dominant systematics in the final distance measurement. Yeah, there is it's not perfectly Keplerian. There's probably like gas pressure or some other kind of support mechanism in there at some level, but it's not dominant, and it turns out that it's still a really good model to assume Keplerian.
Yeah, I guess to that point, this is all so close in that everything is, I guess,
Like
relaxed.
stellar,
right?
like kind of contributions like you worry about for some of these other kinds of modeling aren't a concern here.
Well,
So-
sure, I guess more to the point, you don't expect any significantly elliptical orbits to be present. because-
Well, you could have them, and we do permit ellipticity of the orbits in the modeling generally.
I see. Okay.
That's why I said it's one of the things I'm doing circular here just to keep the picture simple.
Sure.
But it's not too difficult to generalize to like some inclination, warping,
Sure.
ellipticity of orbits. All these things are actually folded into the full modeling.
Mhm.
They're just, I think of them as details on the conceptual picture.
Sure,
But yeah, ellipticity is allowed. It turns out to be very, very small, right? In this system, it's like well under 0.01.
that makes sense.
So a little bit of history of this kind of disk modeling system, or this modeling idea now. So it's the very earliest results that I showed a couple slides back. sort of culminating in this 1995 Miyoshi et al. Paper, did this kind of disk modeling. They really tried to back out the mass and the distance of the system, but they did it in what I think of as kind of a piecewise manner. They looked at sort of different components of observations, like maybe the velocities in this position velocity diagram, or the accelerations in this kind of monitoring approach, and tried to stitch together like, okay, we can constrain the dynamical center using the velocities, and then we can go ahead and measure the radii of the systemic features using the accelerations. And if we assume those radii are comparable to the high velocity features, we can sort of back out the mass and the distance that way. This is the kind of approach that was taken in these early papers. But the first, what I think of as fully global, self-consistent kind of modeling actually took place also here. Jim Herrnstein was a PhD student in the 90s here under Jim Moran, I believe, and really carried out the first kind of approach that took all of these observations, the positions, the velocities, and accelerations, incorporated them into a full model that got both the mass and the distance of the system constrained independently. And this was the first of what I think of as the kind of precision distance measurements to the system. This work achieved a 5% distance measurement precision, which is already really quite good, really incredible for an extragalactic system. And then there was an enormous amount of work that was done over the following decade and a half, also by a group here at the CFA, including people like Jim Moran, Mark Reed, Lincoln Greenhill, and a couple of, I think, postdocs at the time, Alice Argonne and Liz Humphreys. They took, I think, about 20 additional epochs of VLBI data on this system, really did a lot of tour de force in observation, data reduction, calibration, all what have you, right? A lot of VLBI work, and they published a series of papers on this. They culminated in this 2013 paper led by Liz Humphreys, which achieved then at the end of that all a 3% constraint on the distance of the system, so improved the precision quite a bit. And this was now dominated by systematics in the calibration and the data handling. And the statistical uncertainty was subdominant in this error bar. And so that's something that was tackled in the subsequent years, culminating in this work in 2019, led by Mark Reed, where now these various calibration uncertainties were folded into the model alongside the physical model for the system. That allowed us to marginalize over these uncertainties and really reduce the systematic component of the error bar down to the point where it's now comparable to the statistical uncertainty. And the dominant component now is this fact that the model only seems to hold up so well. When you get to this level, it's about 1.5 total percent precision now. It's really the case that we don't think the model is trustworthy below this level. Now we're seeing deviations that are just not describable by the model. You have to inflate the noise or something to account for this. And so I just pulled this quote from Herrnstein's thesis work showing that even at the time, he recognized, okay, this is going to be really important for cosmology. They were thinking about Cepheid variables at the time. It's really interesting to think about the context in which that work was done. The 90s grad school here at CFA must have been very exciting. Adam Rees was also a grad student here and doing the work that culminated in the discovery of dark energy. So I think they were all talking to each other and thinking about cosmological applications all the time here. And this showed up in the thesis work. And it's basically like this distance measurement, it was 5% at the time, now it's 1.5%, but a precise extragalactic distance measurement is going to be super useful for doing things like calibrating these standard candles that are used in cosmology. And that turns out to be very, very correct. And it's actually probably the primary utility of this system now is as a calibration anchor for these other distance measuring techniques that are primarily used in cosmology.
So with these sorts of sources, how far can you go in redshift?
Yeah, so
Or is
I'm
it
only
just-
talking about NGC 458 so far. We go in redshift to about a little less than 0.1 at the moment. I'll talk about those sources in a few slides.
Okay.
I'm still not talking about any major source other than NGC 458 because it's a good one. It's worth spending some time on. But okay, so this one we have an absolute distance to. What I mean, we have a geometric, or we basically use gravity to measure the orbital radii of the masers in the system. We use VLBI to measure the angular radii of those same orbits. And we're basically just have a big skinny triangle and we're doing trigonometry to get the distance of the system. It's sort of a fundamental type of measurement. It's not really doing any sort of empirical calibration of anything else. It's kind of just using fairly standard physics. And this is very unique for an extragalactic system. The NGC 458 is also a big galaxy. It hosts a lot of things besides this AGN and this maser disk, including Cepheid variable stars and stars that are at the end of their lives up at the tip of the red giant branch. These two categories of things, among others, are used as what are called primary distance indicators or primary standard candles in a cosmological framework. And Cepheid variable stars are the most well known, but basically there are others like the JRGBs and Myra variables and other objects that are used as what I think of as standardizable candles. They seem to obey some empirical relationship between something that's easy to measure, like the period of variability or the color in a color magnitude diagram, and the absolute luminosity of these objects. And so if you can calibrate that empirical relationship, meaning you know the distance to some of these things in some system, where you can get the absolute luminosity and thereby get the 0 point of this relation, then you can apply it in many other locations and get distances to other objects as well. That's what's done in this sort of cosmological work. These Cepheid variable stars, these stars at the tip of the red giant branch, are also located in many other galaxies. Some of those galaxies host what are called secondary distance indicators, or secondary standard candles, the most famous of which are these type 1a supernovae. And so if you have a galaxy that has a bunch of Cepheid variable stars, maybe it also has a type 1a supernova go off, those Cepheid variables were calibrated in NGC 458, so you know how to turn their periods into absolute luminosities and therefore a distance to that galaxy. And so you can calibrate the type 1a supernova distance to, in this case, some kind of light curve relationship. There's this Phillips relationship that they use determining the decay rate with the peak flux of a type 1a supernova. And similarly for these other kinds of techniques. And then these objects, type 1a supernovae and their ilk, are located far enough out there and in sufficiently large numbers that we're able to basically use them directly to constrain cosmology, the Hubble constant, the deceleration parameter. And this is the distance ladder approach to doing cosmology. And I want to just pause for a moment, because at the foot of this, you need to know a distance to something at some point before you can calibrate all this stuff. And I think it's easy for us to overlook. It's these people who aren't steeped in this trying to measure distances to things world. It's easy for us to overlook just how unusual it is that we can measure the distance to an extragalactic object. It's really the case that the vast majority of distances extragalactically are using some sort of empirically calibrated relationship between luminosities or some sort of fundamental plane or something like this that are ultimately have to be tied somewhere to an actual distance measurement that didn't assume any of that stuff. And NGC 458 is a very unique system in this way. To give an example that we know about is M87. The distance to M87 has been measured using surface brightness fluctuations and using stars at the tip of the red giant branch. If we have the distance to NGC 458 wrong by some factor, that means the distance to M87 is also wrong by that same factor, right? Because these things are all calibrated based on that distance. So, and it's not just true for M87, it's true for every galaxy in the universe, right? If you get that wrong, the whole universe gets bigger or smaller. It's a weird thing. It's a scary thing. I'm scared by that. But unfortunately, I'm lying a little bit. And it's that we don't just rely on NGC 458. In particular, for the Cepheid variable stars, there are another couple of categories of really geometric distance calibration that we can use to anchor that 0 point. There are Cepheid variable stars inside of the Milky Way, so we can do sort of normal Earth-Sun parallax to get the distances to those and calibrate the relationship there. And then also in the Large Magellanic Cloud, which is almost in the Milky Way, but is technically extragalactic, there are a bunch of eclipsing binaries, and if you can use these eclipsing binary star systems are also a kind of geometric tool that you can use to measure distances. And so we can measure those in the LMC, and the LMC is a little bit complicated because it's so close to us that its sort of depth into the sky is not negligible, and you need to kind of worry about that. But basically, effectively, you can say if you know the distance of the LMC using these kind of eclipsing binaries, then you can measure Cepheid variable stars inside of the LMC and calibrate them that way, modulo some corrections for the depth of it and all that stuff. But that's it. That's the extent of my lies. Right now, this is complete. And it turns out that there are some categories of these things where you really can't do anything inside the Milky Way or in the LMC. Right? For instance, the tip of the red giant branch stars rely on having a big population of these things sitting in the same place. We're in the middle of the Milky Way. We can't use this kind of color magnitude diagram type of technique to assess TRGB stars. We need to look at them extragalactically. And the same for things like surface brightness fluctuations. Go ahead, Ramesh.
So the Milky Way parallaxes for Cepheids, did Gaia make a huge improvement in that accuracy?
I don't think it made a huge improvement because they had really, well, I think this is really an Adam question. I think the big reason for that is because they had so much dedicated time on HST that they used to look at each of these objects and really do sort of dedicated parallax on each individual Cepheid that they had in the Milky Way that they cared about. And they did this for a few dozen objects. And Gaia sort of just confirmed that that was being done properly. But Gaia's the whole point is to do it for 1 billion objects. If you had the time on HST, you could do it for a few. And I think that's basically what they did.
Okay.
Yeah.
HST had cleaned it up.
HST had already cleaned that up fair bit. They had used Gaia and compared with it and shown, I think Gaia collected a bunch more of them and helped with the sort of statistics of it all, but I don't think it improved the parallaxes of those best measured systems very much, if at all. And the eclipsing, but once you get to the LMC, Gaia's not even really helping you.
Yeah.
All right, so anyway, we're still in the situation where 4058 is playing this very outsized role in calibrating this whole set of systems because there's this whole branches here that rely entirely on it. And so if you're scared by that, I'm scared by that. I think what you want, why am I scared? The reason I'm scared is because there's effects you might care about. There's effects you might be worried about, right? These Cepheid variable stars, again, we don't have a first principles understanding of what's going on. We have some qualitative explanation for what's going on in Cepheid variables. In type 1a supernovae, it's even worse. But we aren't able to derive the period luminosity relationship from first principles. as you might worry that there are things that influence, right? If it's this sort of opacity in a stellar interior kind of effect, maybe metallicity matters, or maybe the age of the star matters. These things kind of matter. If you're looking at just a very, very small number of stellar environments, calibration of the Milky Way, calibration of the LMC, calibration of HC 458, but you're applying it to dozens or hundreds of other galaxies that have totally different environments that you don't know anything about, you might worry that these are things where that calibration in one location doesn't apply infinitely well to a calibration in another location. And so what you want is you want some way to either calibrate these things in many, many environments, or you want a way to bypass the need to do this calibration at all. And so what you want, what I want, what we all want at the end of the day, is more systems like NGC 458. And so that's what a lot of people tried to look for. There were a bunch of surveys in the 90s and the early 2000s. I'm not going to go through all of these, but using things like OVRO, using things like Parkes Telescope, Effelsberg, the Deep Space Network dishes, a bunch of others, just trying to find Nobayama, trying to find these more systems like this. And by the fruit of all this labor, by the end of the sort of 90s into the early 2000s, there were about 25 systems known, most of which were not these disk type systems, but like megamasers associated with AGN in some way. And what really changed the game here was the completion of the Green Bank Telescope in West Virginia. This is a plot that I stole from Jim Bratz, showing the rate of discovery of these maser systems versus time, and colored by which telescope is doing the discovering. Once the GBT was done commissioning in the early 2000s, the GBT is now shown in green. The number of detections increased really dramatically, and now the bulk of these systems have been discovered using Green Bank Telescope, and there's something like a little over 200 of them that are known, some small fraction of which are these nice disk systems that could be used for making these distance measurements. And here's a comparison I'd like to show. This on the left is one of these spectra for just one of these other maser systems now, not NGC 458, one of these more distant ones, typically of order 100 megaparsecs is a typical distance for one of these things. Showing what these spectra look like.
Are these all around supermassive black holes?
All of the ones that I'm talking about are going to be in these kind of accretion disk environments around supermassive black holes on scales of about 1/10 to 1 parsec.
So we could argue, you could argue that you can't really get this kind of signal from an object other than a supermassive black hole. Is that true?
I think it has been argued. Yeah, without spatial resolution, one can say like, okay, you've accumulated, this kind of star formation maser kind of idea that you accumulate many small sources of emission into one in aggregate big source. But once we have the resolution here, and if you see this kind of variability, I think that the arguments are pretty good. This needs to be powered by something more energetic. But okay, so these just comparing the spectra on the left is one where I think this was Effelsberg, showing the kind of quality of spectrum you got for a typical integration pre-GBT, and now post-GBT you get something much better, really able to detect these systems much more easily, and also probe the finer scale features in them, which is really important for making the kinds of measurements I was talking about. So you have a bunch of these systems out there. Go
The
ahead.
previous one, sorry. So here you're also, so you're saying that the 3.2K, that's the high velocity line, is that right? Or the
And over here,
blue
would be
shifted
the
or
high
red
velocity
shifted?
emission. What's that?
the blue shifted and red shifted
Yes,
components?
the red shifted and blue shifted emission in this system.
Okay, and this big peak
And
is
the
actually,
central peak is the systemic, the
Oh.
ones that be on the line of sight to the black hole. Yeah, same as the picture from before, but it's for another system now.
and you're also saying that you have the angular resolution enough to actually show that these are localized, and like you said for NGC.
Yeah, I'll show VLBI maps in a moment
Okay.
I don't think I'm showing you for this system in particular, but I'll show for a
Okay.
few. And you'll see, yeah, we get the resolution in order to see them. Not as good as 4050 because they're farther away, but we do have the resolution to do it. But okay, just sort of closing the thought here is that if you have access to all these systems now, and actually the same kind of maser-based distance measurement approach applies to all of them, you can just bypass this whole distance ladder bit entirely. Each of these objects now gives you a distance measurement by itself without needing to sort of daisy chain a bunch of calibrations with one another, and you get directly into the cosmological parameters by just measuring a few of these things. And this is exactly the idea of the MegaMaser Cosmology project. And I've already gone through pretty much, I think, all of these ideas. Basically, what we're trying to do is measure the Hubble constant directly using these maser type systems out in the Hubble flow, skipping a whole bunch of business associated with standard candles and distance ladders and all that. Just showing some of the faces. I think some people don't know, a lot of people on here, the MegaMaser Cosmology project is led by Jim Bratz over there at the top left at NREO. It is an international team. It's a lot smaller than something like the EHT collaboration is. Instead of hundreds of scientists, it's sort of like a dozen folks. And you may recognize some of these folks, but it is an international team. We're still doing VLBI. In some ways, it's very similar. And sort of quantitatively, the goal of the MCP has been to measure the Hubble constant primarily to a precision of about 3%. And so this can be achieved, you just do the statistics. You can get sort of an order 10% measurement to order 10 systems, or maybe a little bit better to somewhat fewer systems. And you can get this kind of measurement. And I think it's natural to wonder why are we so not ambitious here, right? Why are we going for 10% measurement precision on individual systems when I just bragged for like 20 minutes about how we got a 1.5% measurement precision to NGC 458, right? Why are we settling for so much less for each of these other systems? And the answer, as it often does, comes down to angular resolution and sensitivity. So here is now in physical scale. So I have a parsec-scale bar there on the bottom, showing the Maser disks are real VLBI maps of each of a number of systems. NGC 458 on the top now, and you see a bunch more Maser spots there because this is now the more modern measurements using all of the accumulated data from that CFA effort I spoke about. But then a number of other of these systems that are located much farther away. And it's interesting, in physical size, they're all pretty comparable to one another. They're all something like a parsec in size, maybe a little factor of 2 larger than that in the biggest cases. But if we go, this is the physical size, right? The way they look on the sky, most of these things are much more distant than NGC 458, right? NGC 458 is about a distance of 7.5 megaparsecs. Typical distances for these things are more like 100 megaparsecs. They're much farther away. So in addition to being much fainter, right, like that spectrum I showed, they're also just smaller in angular size. And if we plot up here a relevant piece of comparison, which is the 22 gigahertz of VLBI resolution element, we're typically using the VLBA, you see it's actually kind of comparable in some size, particularly if your disk, I oriented them all horizontally here. On the sky, they got a random orientation. You can get aligned with that thing. It can be a big mess. Basically, you have a problem. That's like what happened with this one, for instance. You see how that's more uncertain. There's a bunch of scatter in there associated with the alignment of the beam. And so each of these systems are individually much more poorly measured than NGC 458, and we have to combine a bunch of them in order to get the best constraints on any cosmological quantity, in particular the Hubble constant. And so that's what went on. We combined, there's half a dozen of these objects that have been measured through this program so far. Go ahead, Ramesh.
So these are all nice edge-on systems.
That's right.
There's surely a selection effect which preferentially picks out. So is the whole catalog all edge-on systems?
That's right. Yeah. So this is, I think, the same kind of effect I talked about with the velocities.
Yeah.
We think is the same kind of thing driving the selection towards edge-on systems, is that you maximize the path through the material and you sort of get this really strong amplification. Almost certainly, there's a whole bunch of them out there that aren't edge-on, right? They're just
Right.
pointed in different directions, basically.
Right.
You just don't
But
see
you
them.
have hundreds, which, GPT.
No, so
how many of those are edge-on?
Yeah, so of those, these edge-on disk systems constitute about 20. It's only about 10% of the total sample. Yeah, no. So many of them are not these kind of nice. So you get some of them that only show the central features, right? We don't see the high. There's a number of, and there's variants that were like there's clearly some non-disk interaction, like there's some shocked region of gas nearby, maybe with the jet hitting the ISM or something, or there's Maser emission from something that isn't one of these disk systems, but is close by in proximity to the AGN. So many of those, that's its whole own talk of the sort of population of these objects. I'm really zooming in on the best examples here, just looking at the disk systems for which we really feel they're not particularly contaminated by sort of non-Keplerian motions, at least at the level that we can measure here. So just looking at how these look on a Hubble diagram, here's the distances measurements versus the velocity. We're able to place a constraint when combining all of these things on the Hubble constant of a little bit shy of 74 kilometers per second per megaparsec, with an uncertainty of about 3 kilometers per second per megaparsec in that measurement. This is very admittedly not the most precise constraint on the Hubble constant. The whole shebang of the distance ladder with all of the standard candles and everything involved collectively gives you a constraint on the Hubble constant that's about 73, plus or minus about 1 kilometer per second per megaparsec, much more precise than this. But of course, this is completely independent of that. This is something where we've bypassed all of that entirely. None of the sort of tangled web of calibrations is relevant here. So this is a really nice confirmation that that is not getting lost in the woods somewhere when it's doing all of that work. And then actually, when you do it totally independently, you do get a very consistent constraint. And then I'll also say, because it's popular these days, that this measurement is a reluctant participant in something known as the Hubble tension, which is this fact that apparently these low redshift measurements of the Hubble constant with standard candles, with masers and other techniques are tending to find a value of the Hubble constant that's a little higher than 70, like 73 or 74. Whereas cosmological microwave background measurements, which can predict the value of the Hubble constant, assuming a cosmological model, can get something that's more like 67 with, again, a very small uncertainty. So that's something people call the Hubble tension and spend a lot of time thinking about. But we're not very interested in that here, right? We're just thinking about other things. You probably won't have escaped your notice that the Mega Maser Cosmology Project sample size is pretty small, right? These things are pretty rare. And so the best way to improve this kind of measurement is going to be to increase that sample size. And the question is, how do we do that, right? Looking forward, how do we actually get more of these objects to measure? there's a whole train of thought that goes into thinking about how to improve the surveying. So the way in which these AGN have been selected has been changing throughout the years. Like the ones that we're pointing our radio telescopes at in the first place to try to find these objects. You can imagine improving the way we select. Right? There's just like bajillions of galaxies out there, right? How do we choose which ones to point at? That'll improve. We can improve our detection rate there. We'll improve the efficiency with which we can find these systems and follow them up and all the downstream stuff. But something that I think is a sort of more of a guarantee in some sense is that we're definitely going to be having some next generation radio facilities down the line. In particular, I've got my eye on the NGVLA. That's going to be another factor of 10 boost in sensitivity over the GBT or the VLBA. And so we saw the comparison between pre-GBT and post-GBT spectra. I imagine we're going to get some similar boost when the NGVLA comes online. I have some synthetic spectra down here on the bottom showing what an hour of observing with the GBT looks like on the left versus what we think an hour of observing with the NGVLA will look like on the right. We're seeing I've zoomed into the bottom here, we're seeing a much wider range of velocities spanned by the high velocity features. That means that we're really going to be able to trace out that rotation curve over a much broader span, really get the curvature of that, constrain the dynamical center of the system, and really help to cleave that degeneracy between the mass and the distance. That remains the dominant part of the modeling uncertainty for most of these systems. Another thing that I like a lot is that 22 gigahertz masers, this rotational transition of the water molecule that I've been talking about the whole time, isn't the only transition of the water molecule. In fact, the water molecule has this rich spectrum of energy levels. This is just the ground vibrational states, rotational transitions for the water molecule. This is the simplest version of the water molecule's energy level diagram, energy there in Kelvin on the vertical axis, and some angular momentum quantum number here on the bottom. And I've highlighted the 22 gigahertz observations transition between two of these levels, but there's a bunch of others that actually are expected to exhibit or be at least amenable to maser activity under physical conditions that are similar to those that produce 22 gigahertz emission. And in particular, I'm very excited about the 321 and the 325 gigahertz transitions, both because those are more than an order of magnitude higher frequency than the 22, right? So if we could do VLBI of transitions of those ones, you're talking about angular resolutions that now look an awful lot like what we get for NGC 458, but for systems that are 100 megaparsecs away rather than 10 megaparsecs away. And also 321, 325 are in ALMA band 7. ALMA band 7 is something the EHT is offering observations in, right? So actually there exists a VLBI array capable of doing observations at these frequencies in principle. And it's just a matter of us finding the right targets. And they're not just theoretical. Go ahead, Prashant.
How did you get a larger distance with the higher frequency? Sorry, I missed that.
Sorry, the angular resolution
Okay, I see.
is finer by a factor of the frequency ratio. And so our physical size scale that we probe is just going to be comparable in distant systems with these frequencies to what we have now for 4258. That was my only point.
Maybe Bex needs to do a little.
Well, I mean, I'm not going to say no. But all right, thanks, Peter. Just to say, these things aren't purely in the line of theory right now. We got observational evidence for these high frequency masers. So here's a couple examples of spectra taken with ALMA for a particularly bright galaxy. This was targeted because it's very bright, not because it's a good distance system. It has an AGN disk system maser, but it also has contamination from an outflow that makes it really difficult to actually make a good measurement of this system, but it serves as a good test bed for identifying which transitions are likely to be the most promising. So there's one of 321, the 183, and actually sort of in the ether up here, we do actually have 325 gigahertz observations of the system as well, comparable set of spectra. So we know that all of these transitions are existing and are exhibiting bright emission in these systems. There's now been more recently a survey that's been carried out. This was the sub-millimeter masers, and we're seeing a lot of these systems. These are all fairly faint, unfortunately, the ones that have been uncovered so far at the level of tens of millijanskys or less.
So Doc,
Go ahead.
but these are not the same systems which produced 22 megahertz.
They are. This is the critical thing. This survey was carried out. I was about to say the survey was carried out. The detection rate was very high, about 60 to 70%, because it was carried out only on systems that were known to be producing 22 gigahertz emission already. So we have a good, the prediction is there, and now we have a pretty good observational evidence that if it has 22 gigahertz megamaser emission, almost certainly it's having some of this sub-millimeter megamaser.
4258, does it have it?
This is a sore point from you, Ramesh.
Sore point, it doesn't.
No. We haven't pointed that. It's worse than it does.
That is terrible. The first and best golden guy.
And the reason we haven't pointed at it has nothing to do with a lack of proposal writing.
Okay.
I may just leave it at that for now, and I'll wrap it up and come back to it at the end. It is a sore point.
Is this the guy that Alma cannot point? Oh, yeah, you told me about that. It's a little bit too low in the sky.
8 arc minutes too high, is what it is. Actually, 18 arc minutes too high in 2000. It's more like 8 arc minutes too high right now.
Oh, you just have to wait.
The precession of the Earth will bring it within almost declination limit in 2055. It's a super one.
You've done all the
That's all I've
calculations
got.
clearly.
Wow.
That's the whole thing. I'll put the summary slide. I'm done there. There's some millimeter mission number I'm looking for now in between now and the next generation facilities. Thank you. Then we can talk about agency work to date sub-millimeter.
Okay, we have about 5 minutes for questions, so questions. I'll go
Okay, fine.
So I'm curious about like, in terms of extending these kind of like low, like measurements with low number of steps in the ladder to further distances, is there any like hope or like something to find, like a standard rod, standard something in an agent and like to.
These are kind of a standard ruler.
Yeah,
so it's
but this you can, I mean, you say like, you can hope to get like a redshift of 4.1.
Yeah.
But like to go further, can we like try finding something like bright age, I mean, in these agents and then like use bright agents that we can see like the redshift of like.
Yeah, so I think there's a lot of hope, right? So
Yeah.
one interesting kind of system are these type 2 supernovae, which can, some of them can be modeled, right? They have an expanding shell of material that's going out, and that can be, people claim that that could potentially be modeled well enough to act as a kind of standard combo, standard candle, standard ruler. I haven't seen it done very well yet, but I think there's people working on that, and that's certainly a thing that could be seen to high redshift. On the maser side, which I know more about, well, so there's also lenses, which I haven't gotten into, gravitational lenses, which are their own interesting high redshift probe, but they that are kind of a standard ruler because they can measure the extent of the lens itself using the mass modeling. But on the maser side, one thing that's really interesting that I haven't talked about at all here, but that there's just been initial forays into are lensed masers, which get to very high redshift, and so there's some very promising initial work showing that some of these lens masers can access the very, very strong maser transitions. This one that I didn't spend a lot of time talking about, this 380 gigahertz maser, which sits in the middle of a deep atmospheric trough, but a high redshifts out of that trough, and you can actually observe it with ALMA or something. And this one, if it's redshifted into some more reasonable range in band 7, right? So redshift of a half or something like this, where it gets you down to band 7 or band 6. Then you can actually start to talk about doing these kinds of measurements on systems that are at very high redshift by virtue of having been amplified and magnified by a lens.
Yeah, I was,
But I think
something like more AGN specific in mind, like maybe something in the jets.
Yeah, I don't know of any standard ruler type phenomenon in the jets.
Yeah.
They may exist, but I'm not aware of any.
Can I insert myself and
Okay.
then can go? Can you say more about why you need the supermassive black holes to power these?
So I didn't say anything about the powering mechanism, really. It's really the area that you need. You kind of need the total volume of of material to produce the maser. And in circumstellar type of, so you need a large, I mean, imagine if you could set it up yourself, right? You want a sort of medium where it's kind of totally not moving with respect to itself, and you just have the sort of gain path by which the photons can come in one side and amplify forever and come out, shoot out the other side really, really bright. And having a big system like this that's sort of velocity coherent for a long period of a long spatial region is really hard to produce in like a circumstellar environment, right? Because around a star, you kind of have AU scale things going on, and on scales of tens or maybe hundreds of AU, you have pretty substantial changes in just the medium and things. It's really hard to accumulate this kind of gain path. The nice thing about a black hole is it can sort of dominate the dynamics in a region that's ordered parsec in size and really produce these very big. So it's not so much the energetics of it, although we do think that's involved in sort of heating the gas and ultimately helping it to pump the system. But really it's the velocity coherence, the very large scales that you need to access in order to get these gain paths and amplify to this level.
Okay.
That's really why these AGN accretion disks are the sort of environments where we think we're seeing them.
Not like specifically black holes, any compact object in principle.
Exactly.
Like, probably black holes.
Probably, but like a stellar mass black hole wouldn't do the same.
No,
right?
I mean, if there is something like,
if you had,
new physics and whatever.
Sure,
Yeah.
right. If you have something compact enough to basically be
Yeah.
indistinguishable from parsec away from a black hole gravitationally, then yeah, it would have the same effect.
Let's do-
Maybe this is a bit of a follow-up. I was wondering about the structure of these lumps of amazing gas, what it was like, and what keeps it so compact and coherent.
Yeah, so I think we're really, the physics of these masers, especially the mega masers, is really, I would say, understudied and relatively poorly understood. Observationally, we know that they are extremely compact. So this NGC 458 system, in addition to being fabulous in so many ways, has the claim to fame of being the only object for which radio Astron was able to detect it on its longest baseline. Right, so it was out basically 30 Earth diameter baseline, all the way almost out to the moon. and it was able to detect maser emission from this object. So that's really, really compact. I mean, that's the fringe spacing of like 7 or 8 microarc seconds. It was seeing like Jansky level emission from that thing. Really compact, and there was some resolution there tangentially from one maser spot to the other. But it seems that there's these really compact in our plane of the sky regions that are also very cool in a sort of gas thermal sense. Like they have a small scale height in the disk. The disk in 4058 has been constrained to be, I'm trying to remember the spatial scale associated with it, but basically the full width F max is something like 5 microarc seconds, and compared to 5 milliarc seconds ish total radial extension. This is an aspect ratio of like 1,000 or something ridiculous. It's really, really cool, and we don't know if that's actually the total, like the center of the disk and all the gases obeying that kind of thing, or if it's like some kind of skin of water on otherwise maybe a fatter disk. I think we just don't know because it's the only probe we have of the gas there at these scales. We don't have anything else to compare it to. And so it's really hard to discern how much of it is just saying you're seeing the product of this totally nonlinear maser amplification process, and you just get the shape of the beam that produced, versus you're actually tracing the bulk of the gas structure in some way. And probably it's more like the former than the latter. Not sure if that really answered your question.
Yeah, so it has maybe quite a bit of depth.
We think it has a fair bit of depth, yeah, because it has to for the gain amplification, but we can't sort of discern any extent in the plane of the sky.
Can we do Prashant?
No, I have asked mine.
Go ahead.
So you have now got, a collection of these objects.
Yeah.
What are the masses of these?
Yes.
Distribution.
Yeah, so it's a fun thing because basically, for some reason, added to the list of things we don't know, almost all of the masses are about 10 to the 7 solar masses within a factor of maybe 3. Maybe they're not like, we're not seeing 10 to the 7, 10 to the 8, 10 to the 9 solar masses. They're all like a few by 10 to the 7, or maybe like half by 10 to the 7, so like a few by 10 to the 7 solar masses.
And this has to be something.
It has to be something to do with
physics.
yeah, exactly. It has something to do with the life cycle of the AGN in which these things are able to arise, or so somehow it's telling us something about when we can observe these objects.
You would love to see that.
I would
nine
love to
guys.
see
They see them much further.
Oh
right?
my goodness! And there's predictions for what these giga masers would look like at very
Yeah.
high redshift, around 10 to the 9 solar mass black holes. Maybe the physics back then was more conducive to having them around the bigger black holes. But as of now, it's just not happening. All of them, for which we can measure the mass about 10
So
to
then the
the
question is, you've got, as you say, a zillion transitions.
7.
Maybe some of those actually would like the bigger black
It
holes.
would be fantastic.
It would
Yeah,
be.
I think it was a totally underexplored territory right now. We're just scratching the surface, trying to scrounge up all the time to actually observe these things and getting it, 15% of the time. So it's a lot of work to even get one of those surveys that I showed was like took ages to get the all the time for that together. And it's just one transition with a bunch of systems. But yeah, I would love to do like full ALMA sweeps of many of these targets. It's just turns out to be a lot of time.
You have time?
Yeah, go for it.
So following up on Ramesh's question,
Yeah.
so you're saying then that the radius at which these things are also emitting should be roughly similar because the masses of the central objects are also roughly similar.
Yeah, so that's why we saw these disk sizes were all kind of comparable. Right? I think this is part of the reasons because the masses are all very comparable.
Okay, that's cool. Okay, so the other question I have is why only water transitions? Can you have other transitions and then fill out more?
Yeah, so I spent a
more
good
lines?
chunk of my PhD time thinking about this and
Uh-huh.
looking for some of these other, there's other species that are known to maze, SIO, right?
Yeah,
Silicon
exactly.
monoxide, OH is able to do it, even methanol and some more
Uh-huh.
complicated molecules can exhibit maser activity. In certain environments, even hydrogen and things can do it.
Right.
We did some searches in a number of these systems, including 4058 for any of these things. It's never been picked up before, but I don't think we have a good enough. I mean, the modeling of these sort of molecular disks is very, very difficult. There's like astrochemistry involved in
Yeah.
actually determining the sort of states of all of the molecules and whether any of them could really be conducive to supporting a maser. I think it's totally unknown whether we should even expect other species to be mazing. Empirically, there's a limited piece of evidence that we don't see any in a few systems that have been checked for a few transitions, but I consider it to be a very open question. So
No,
Are there CO masers?
exactly.
there are some CO
That's
masers,
right.
yeah, but none of
That's
these.
a nice.
That's the question.
Form and molecule.
Exactly.
Yeah. Well, so, I mean, yeah, a lot of these, all of the common elements like SIO, CO, OH, all these are common molecules.
Yeah.
But and water is pretty common as well. But it'd be anything that's got one of these common
Yeah.
small molecule with one of these common atoms in it is pretty common in these kind of gas systems. But no, we haven't seen any CO masers in these AGN. They've only been seen
Ah.
sort of in sort of Milky Way type. This is what I mean. Masers have been seen in all of these species, typically in the Milky Way in like stellar type environments. Star forming or a system that has a lot of fun masers are actually the envelopes, the sort of outer atmospheres of these evolved stars. Right? These stars puff up, they get really big, their outer edges cool, and they get all kinds of interesting molecules in there that can do stuff like this. And they're pretty big as well. There are many, maybe hundreds of AU across, so you get these large gain paths for inside of the Milky Way.
Are any of these in the NGVLA bands? Like-
Yeah, the one
So
up
with
to
high
the-
sensitivity, could you see some of this? Like
Yeah, so I think SIO, right? The
Okay.
SIO masers at 86 gigahertz
86,
are
right.
very much in the NGVLA band, the high band of NGVLA.
So these stellar envelopes should look like amazing rings, right?
Yeah, and they do.
Sure.
Yeah.
I see.
They're basically these rings of that's exactly what they look
That's
like.
cool.
Yeah.
Not terribly cosmologically useful, but.
But they're cool. They're cool. Exactly. Totally different kind of environment. Yeah,
Yeah.
but they're cool. They're very cool, and we should look at them more. We should always look at them.
Okay, well, join me in thanking Tom once again. Thank you for a great closing to our
Yeah.
seminar series.
Wow, I still think.